This lecture is going to focus on part 2 of linear kinematics, mostly looking at speed, velocity, acceleration, and the multiple modes and methods that we use to calculate these values in certain scenarios. In delineating between the difference between speed and velocity, they are both measures of rate of motion or rate of change of motion, how fast the body or some object is moving. They're both measured in meters per second, so that is something that you need to know. Now, the main difference between speed and velocity is that speed is a scalar quantity, so as we discussed in class, it is not going to have a direction associated with it, but velocity is a vector, so it will have a value and a direction. Now, one thing that's important to note with equations that we're going to look at with speed and velocity, speed is actually denoted as the change in distance traveled over a change in time, but distance is actually used or written as an s. So this would actually equal change in s over change in time, where velocity is going to equal change in displacement, and that is going to be your change in d over change in time. So two major terms that we're going to talk about with speed are average speed and instantaneous speed. Okay, so average speed is going to be your total distance over your total time. Okay, this is used a lot in sports. Obviously, the speed of a person, how fast they're moving, or even the speed of an object over a certain amount of time can be very beneficial in sport and exercise, right? But a lot of times this average speed doesn't give us a great indicator of what's really happening across a given amount of time. So something that is done a lot, especially with races or any kind of sport event in which there's, it can be broken down into intervals or pretty good segments. A lot of elite athletes break these down so that they can really see what's happening throughout their event. So this table, it's in your book, and there's a good explanation of it in your book as well. But this is a table depicting the time intervals of every 10 meters of Usain Bolt's 2009 World Championship win versus his 2017 World Championship loss. Okay, now you can see down here his total time for each race was 9.58 and 9.95. And if you were to take that that time interval and calculate his average speed doing 9.58 over 100 meters or 9.95 over 100 meters, you would get his average speed for each of these races. Now, his average speed for his 2017 race wasn't really that much different than his 2009 race, but it was a difference between a win and actually coming in third. So what they did was broke his race into 10-meter time intervals, and they found that his speed, or you could call it his instantaneous speed between 50 and 60 for his 2017 race, I believe, was actually his peak, whereas in the 2009, he was peaking at 70 to 80 meters. All right, and that actually turned out to be the biggest difference in his race times. So even though average speed is a good, or can be a good indicator of performance, especially in sport, it's not always indicative of what's really happening throughout an event or some type of sporting endeavor that can really give especially really elite athletes, a lot more valuable information so that they can improve their performance. Now, even though instantaneous speed is going to be your rate of motion at a very um, specific point in time or a very short interval of time, especially in some type of race, it can actually really give you some good information about, especially when an athlete may be peaking, they're like hitting their highest speed or highest velocity in a given interval or event. And just so you guys all know that, I mean, this should be pretty common sense, but average speed, while it's a good indicator of what's happening overall with a certain event, it's the average, right? So obviously that's not going to give you information about what the peak is or the highest velocity or speed that an athlete reaches. So this instantaneous speed or velocity can be helpful in that sense, especially knowing when an athlete hits that speed or that peak velocity throughout a race so that they can either improve or see an improvement within a certain event. So acceleration is the rate of change in velocity. It's going to indicate potentially slowing down or speeding up, but mostly a change in direction or a change in direction of motion. Okay, so again, this is a vector quantity as well. And for velocity and acceleration, we will be using or able to look at resultant velocities and accelerations so that a squared plus b squared equals c squared formula that we talked about with basic trig in the first part for linear kinematics is still going to come in handy, especially talking about launch angles of objects, etc. So just keep that in mind when you're watching this lecture. But going back to acceleration, it is the change in velocity over the change in time. Okay, so it can also be expressed as the final velocity minus the initial velocity over final time over initial time, or it should be overall time. Okay, it is expressed in meters per second squared. Okay, and that is because you are calculating meters per second or change in velocity over time, as you can see right here. So this is going to essentially be meters per second per second. All right, so that's why it's going to be per second squared. Now, one thing that's important to note about acceleration is first of all indicating what your positive and minus directions are. Okay, so for this particular chart, we're going to look at positive direction being towards the right, negative being towards the left. Now, with acceleration, it is possible to have a negative acceleration while still moving in the same direction, meaning your velocity could be positive while your acceleration could be negative. Now, what that means is, and we'll just go through each line of this chart. If you are speeding up, okay, you are going constantly in the same direction, all right, your velocity and your acceleration is going to be going in the same direction. All right, so your change in motion should be on the positive side if you're going to the right and actually speeding up in the right direction. All right, now if you are maintaining a velocity in or going to the right, okay, so your velocity is still positive but you are at a constant velocity, that means that your acceleration is equal to 0. All right. No change in velocity means that the acceleration is 0 or the velocity is constant. Okay. Now, if you are slowing down, that does not mean that your velocity direction has changed. That simply means that your acceleration direction has changed. So if you're moving towards the right, you're still going in the positive direction, but now you undergo a change in motion in the opposite direction. So now your acceleration is actually negative, right? So if the direction in which your body is moving is going to the right, but your acceleration is now going in the opposite direction, then you are slowing down, okay? Now, at this point, you have stopped, you've changed directions, and now you're traveling and your velocity is in the negative direction, okay? Now, your change in motion is positive because it's getting greater, all right? But the direction of your acceleration is negative because now you're accelerating to the left, okay? Doesn't mean you're slowing down, it just means you're accelerating in a different direction, okay? Now, again, if you are moving in the left direction, your velocity is negative. You're moving at a constant velocity, so again, your acceleration is now 0, right? But then, say you decide to slow down again, now in the left direction, so you have to change directions again, plant and cut. If it were in a sporting event, you're still moving in the negative direction, but now your change in motion is negative because you're slowing down, which means that your direction of your acceleration has to be opposite that of your velocity, meaning it would be positive because you're still moving left. So this is a good slide that will summarize the chart that we just looked at. So in the case that you're speeding up or starting, your acceleration should be in the same direction as motion. If you're slowing down or stopping, your acceleration is in the opposite direction of your motion, okay? If the sign of velocity and the sign of the acceleration is the same, your body is speeding up, okay? If the sign of velocity and sign of acceleration are opposite, your body is slowing down. So a variable that we will talk about a good bit is uniform acceleration, and that is when acceleration is constant, or there is a constant force acting on some object. Now, this particular environment or situation allows for prediction of future position and velocities of an object, whether it's a person or some type of projected ball or something of that nature, okay? We have two main applications in uniform acceleration. One is vertical motion, where the only force acting upon a specific object is the acceleration due to gravity. Now, that's something that you must remember for equations that we do, especially with projectile motion, because a lot of times in the vertical direction, all right, the acceleration due to gravity is the only acceleration that matters, okay? All right, so in horizontal motion, what we're going to do in our calculations and in our practice problems is that in most cases, when an object is projected, air resistance is too small to have an impact on that object. So air resistance is basically negated in these situations. Therefore, any horizontal acceleration that would be due to air resistance is completely negated for these situations. So these are some important variables relative to vertical motion that you do need to know. VI is going to be initial velocity, VF final velocity. Change in Y is going to be, and this is important, the change in the displacement of an object in the y direction, right? So again, yi is initial position, yf is final position. G is going to be referencing the acceleration due to gravity, which is again always going to be negative 9.81. The reason it's negative, hopefully you will, you should have picked up on this already, but the reason it's negative is because the acceleration due to gravity should always be somewhat pulling objects down. Okay, so, and then delta t is going to be your change in your time interval, and it could be time f minus time I, and the final and initial time should really come into play if we're looking at a specific interval, say between 5 and 10 seconds. All right, so your 10 would be your TF, where your 5 would be your TI. So then your change in time is actually going to be 5 seconds. All right, so that's when that particular term or will come into play. So in calculating velocities strictly relative to only vertical projectiles or vertical movement, the main equation that we're going to use is the final velocity equals initial velocity plus acceleration due to gravity times the change in t. So say that you toss a ball up and it from the time it leaves your hand to the time it hits your hand again, it's 8 seconds, all right? And I want to know what the velocity is at 6 seconds. Okay, so what you're going to do using this formula is your final velocity, or at 6 seconds, is going to equal your initial velocity, which should be 0, plus negative 9.81, okay, times your change in time, which would be 6. So in this case, you would solve for the final velocity. So that is an example of when you would potentially use that equation. Now, just as we might want to look at the final velocity at some time interval, we may also want to look at the vertical position of an object at the end of some time interval. So in this case, we would use, or we would look for the final position in the y direction is equal to the initial position in the y direction. Now, sometimes in these equations, you must determine whether that initial position is 0 or that initial position starts at, say, 2 meters, right? Plus the initial velocity times the change in time interval that you're looking at, plus 1/2 the acceleration due to gravity times, again, the change in time squared. Now, I know this is a really large equation, and it's something that we will use a good bit potentially, but it is something that you'll probably be given as well on exams and quizzes, so don't freak out too much, but you need to know when to use this equation and how to fill in these terms and these symbols. Now, in order to look at velocity at the end of some displacement, say we're not given the time interval in which we're looking at, this is another equation that we can use. So in this equation, it would be final velocity squared equals initial velocity squared plus 2 times the acceleration due to gravity times the change in displacement. All right. Now, again, this is only looking in vertical direction, so it's strictly going to be displacement in the vertical direction. Okay. Now, one thing that you must be careful with in this equation is remembering that these two variables are squared. So if you need to use the square root of something to find the actual VF, that is what you need to do prior to actually completing a certain problem that you're given. So, in looking at kinematic descriptors for horizontal motion, again, we have final and initial velocities, we have final and initial positions, but in this time in the x direction. And again, the acceleration in a horizontal direction is going to be negligible or zero, okay? Because once an object leaves your hand, there is no extra force happening on that object in a horizontal direction, okay? So the acceleration is always going to be zero in a strictly horizontal motion equation. And again, the change in time interval is here at the bottom. Now, say we want to look at, this should actually be horizontal velocity at the end of some time interval. We would again use the equation Vf equals Vi plus acceleration due to gravity times the change in t. Now, however, because A is equal to 0, that completely negates this part of the equation. Therefore, your final velocity is going to be equal to your initial velocity, and what that means is in horizontal motion, horizontal velocity after a object is released from your hand or projected from some method, your horizontal velocity is going to remain constant over time until it is acted upon by another force, meaning it's caught, an object is caught, or hits a wall, or hits a racket, or hits a bat, something relative to that nature. So our equation in calculating position at the end of some time interval in the horizontal direction, again, since A equals 0 and air resistance is negligible, it's going to take out part of these equations. So the final displacement or position in the x direction equal to initial velocity times time plus 1/2 at squared now becomes final velocity in the x direction equals initial velocity times time. All right. So in this case, again, due to A being equals to 0, this indicates that horizontal displacement only depends only on the time at which an object is in the air prior to it being acted upon by another force and just after it is projected from someone's hand, off a bat, or off a table, etc. So again, with our equations, looking at how they change with horizontal projectiles versus vertical, calculating velocity at the end of some displacement, Vf squared equals Vi squared plus 2a times the change in x now becomes Vf squared equals Vi squared, which again indicates that horizontal velocity remains constant over a given displacement. So these are some key points that you need to keep in mind when discussing and solving equations and problems for projectile motion. An object in the air is acted on only by forces of gravity and air resistance. Obviously, as we've said multiple times at this point, air resistance is going to be negated in all of our calculations, okay? Now, one thing that is really important is that you need to consider vertical and horizontal kinematics separately. All right, so that means that if there's someone standing here and they throw a ball at roughly 45 degrees, we will talk about the horizontal components and the vertical components completely separate. Now, this is where your trig practice that we did in class on Monday will come into play, right? Looking at velocities in the x and y direction, especially, okay? So you need to make sure that you apply appropriate equations of uniform acceleration for each direction. Now this table is table 2.4, and it is on page 75 of your textbook. It will be an extremely valuable tool for you as you are completing problem sets, especially for lecture and for lab. Um, it has all of the descriptors down here and what each of them mean, as well as a very useful chart telling you what you are given and what you're trying to find in the equation that you need to use. So the way that you read this is if you are given, say, initial velocity and change in time, and you're trying to find the change in displacement in the y direction, this is the equation you're going to use, okay? If you're given velocity in the x direction, change in time, and you're trying to look at the change in displacement in the horizontal direction, that's the equation that you're going to use, okay? However, if you're looking at final velocity and initial velocity, or if you're given final velocity and initial velocity of an object in the y direction, okay, and you're looking at the change in time, so potentially how long it's in the air, this is going to be the equation you're going to use, okay? So, again, like I said, this will be a very useful tool for you. So please locate it in your textbook, screenshot it off the slide, whatever you need to do to make sure that you have access to this in solving problems in class. So that is all we have for part 2 of linear kinematics, and we will do our part 2 problem set in class on Wednesday and Friday.